Here.
Thank you, Catalina. Okay, just to start. Yesterday I came here just to hear about the talk on accelerators, and they explain you how the free electron lasers work, and the future free electron lasers that will use plasma sources will work. I don't build or work in the field of realizing accelerators. I'm a user. So what's important for me is that they realize very good machines that produce very good or usable light sources that I can use for my experiments, okay? And the light that is produced by accelerators is called synchrotron radiation light. The reason of this name, I will show it to you later, okay? Let's start this way. This is the outline of my speech. So we will speak about light, synchrotron light. I will tell you about the properties. I will show you also the story of synchrotron radiation, because it started long years ago, and now the modern synchrotron facilities are clearly more different respect to the previous ones. Then I want to show you some applications. And since I work in the X-ray field, many of the examples that I will show you will be using X-rays. First of all, let's just remind units, because at a certain point I will start speaking about angstrom, nanometers, giga electron volt, mega electron volt, and so on. So let's try to understand what I'm speaking about. So when I speak about light, I speak about wavelengths, and I define the distance between these two maxima as wavelength, and normally you measure wavelengths using angstrom units. 1 angstrom is about 10 to the minus 10 meters. In some tables you find also nanometers to define wavelengths, and as you well know, nanometers are 10 to the minus 9 meters, and the relation between angstrom and nanometers is that 1 angstrom is about 0.1 nanometers. Then, when I will speak about energy, I will talk about giga electron volt or mega electron volt. These are billions or millions of electron volt, and the electron volt is the unit used to measure the energy of particles, or also of photons and so on. And also, speaking of time, we will go to very small scales, speaking about picoseconds or femtoseconds. So we are in the scale 10 to the minus 12 seconds or 12 to the minus 15 seconds, okay? This is just so we have a common language speaking about units. Okay, let's talk about light. When you think about light, what do you think about? Just the colors that you can see. You can think about a rainbow, but if you give a look to the electromagnetic spectrum, you can see that visible light is just this tiny slice. In the electromagnetic spectrum, you have all wavelengths going from radio to gamma rays. And what changes? The visible light is just, is just this small region here, and between 380 and 780 nanometers. Then you can go to smaller and smaller wavelengths. What changes? As a function of the kind of wavelength, you see radio waves, microwaves, infrared, visible, and so on, you can see what happens. The wavelengths becomes shorter and shorter. Okay? So this means that visible light has a longer wavelength compared to X-rays. And let's look also what this means. You probably know that wavelength, the product of wavelength times the frequency of photons is equal to the speed of light. And the energy of a photon is given by the Planck constant times the frequency of the photon. So what happens? As your wavelength decreases, your frequency increases. This means that X-rays have higher energy compared to visible light. Is this clear? Okay, let's go on. When I look for a radiation source, it's clearly important what I want to do with the source. If I have to illuminate something very huge, I can use also a fire source. But if I want to see small details with a fire source, I will not be able to see them. So in this case, I need a focus source, like let's say like a LED source. I'm surely more able to see small details than using a fire source. But if I want to study very, very small elements, like atoms, I cannot use visible light. I need to use a photon source that is very narrow and that gives me also a huge amount of photons that has what is called a high density of photons. And when we speak of density of photons, we mean brightness. So I need a very bright source concentrated in a small angular spread to see very, very small things. And this is just to define brightness. When I speak about brightness, I say that a source has high brightness when you are dealing with a high photon flux. So this means you have a source that can emit a huge number of photons, and these photons are concentrated on a small area and a small angular divergence. So more big is the divergence of your beam, smaller is the brightness. Bigger is the dimension of your source, smaller is the brightness. So you need to have high brightness, a source which has high photon flux, small source dimension, small vertical and angular divergence. And what is an ideal source? A storage ring, an accelerator, because this kind of structure that is normally, in the past, this was built to perform high energy physics experiments. But as I will show you, this kind of machine produces also light. And this is a wonderful source of light. And when I speak about light, I don't think about only visible light, but I speak about infrared, X-rays, hard X-rays, and so on. But we will see this later. With storage rings, I can achieve all this huge fan of radiations, as I told you, going from infrared up to hard X-rays, only with one machine. So this kind of system produces a continuous spectrum, and as a function of the part of these rays that I need to use for my experiment, I can just select visible light, infrared light, UV light, X-ray light. So this is a wonderful source. In this case, in this lecture of today, we will concentrate on X-rays. Why? Because with X-rays, I can study atoms. And since you see here that the wavelength we are dealing with X-rays is about 10 to the minus 10 meters, this lets you understand that this is very useful to study atoms, because atoms have that dimension. If you want to study something very small, you need to have a wavelength that is comparable to what you want to study. Is this clear? Why are atoms important? Look here. This is what you well know. This is salt. But when you put these small grains of salt in your food, what you're doing is you're just putting inside crystals made of sodium and chlorine. And behind each of these small atoms, you have a nucleus. Inside your nucleus, you have protons and neutrons. Around your nucleus, you have electrons. What is the difference between protons and electrons? Charge. Electrons have negative charge. Protons have positive charge. And what about the mass? Mass of electrons is bigger or smaller than mass of protons? Smaller, 2,000 times. Electrons have a mass that is 2,000 times smaller than proton mass. This is the periodic table, all of you know it. But this shows you that atoms are all over. We are atoms, okay? And it's really very important to study atoms and to study the atomic structure of material, because probably you don't know this, but there's a big difference between the properties of a bulk piece of gold containing a huge number of atoms and nanoparticles where the number of atoms is really reduced. The properties can be totally different. But to understand this, you need to study the atoms contained in your sample. Another very clarifying example. Look here. We have diamonds and graphite. What's the common thing between these two materials? They're both made of carbon. Carbon is an atom that has 6 as atomic number. When we speak of atomic number, what are we speaking about? That's the number of protons in the nucleus. So graphite and diamond are both made of carbon. But from your point of view, they're the same thing? No. If they have to make you a gift, you prefer a pencil or a diamond? And if they're both made of carbon atoms, why are they so different? What changes? What makes diamond so precious and graphite no? Please. The structure, yes, you're right. The structure of carbon in graphite and the structure of carbon in diamond. What happens? In graphite, you have thin layers of graphene, and one layer is attached to the other with van der Waals forces that are very weak. So when you just write with a pencil, you detach pieces of graphene because the forces between these two planes are very, very weak. But when you deal with diamond, in that case, there are very strong covalent bonds. The tetrahedral structure here is very, very strong. You can cut with diamonds also very strong things like inox and so on, because this is a very strong material. So they're both made of carbon, but they have totally different properties. And how can you understand their properties if you don't know about their atomic structure? So using X-rays, you can give these answers. You can say that graphite has this structure, diamond has this structure, and so you can understand their properties. And if you want to realize new materials, you know also what kind of structure they must have if you want them to behave in a certain way. So it's very important to know the atomic structure of materials. Clear? Let's go on. So with X-rays, at the end, you can apply this kind of studies to many, many different fields. You can study meteorites, molecular biology, chemistry, geophysics, solid-state physics, cultural heritage. And at the end of my lecture, I will show you some application in some of these fields. Clearly not done here, done in other institutes, because I made a selection of the best things I found. But first of all, we need to understand, if I want a very bright X-ray source, I need to understand how this source works and which is the best source for me. So these are the questions that you can ask. Oh, excuse me. What is synchrotron radiation? How is it produced? Something about the story, properties. Are there different kinds of sources? How and why it is used? Applications. It's not difficult to understand how synchrotron radiation is produced because take in mind how an antenna works. You just accelerate electrons and you produce electromagnetic waves. But in this case, your electrons are not moving at the speed of light because they are moving in a medium, so they have a low speed. In a storage ring, what happens is that you have a vacuum chamber where your electrons are moving at very high energy. So their speed is near speed of light. And what happens is that you have a totally different emission concentrated in another cone. Do you think that we can produce synchrotron radiation only artificially with accelerators? Or there's also synchrotron radiation in nature? This is the answer. There's also synchrotron radiation in nature. Let's say that this is the Crab Nebula. It is what remains after the explosion of a supernova. And in 1054, Chinese astronomers wrote in their books that Earth was illuminated, daylight also during night, because that light of that explosion reached Earth. At the moment, if clearly with huge telescopes you give a look to this Crab Nebula, this bluish line here, light here, is produced by synchrotron radiation effects, because in the middle of this nebula there is a pulsar that forces the particles in this gas to go on circular trajectories, and they emit light. This is a very important element for astronomers. But synchrotron radiation is important also for us. On Earth, we can produce it. And what do we use to produce it? We use to produce it storage rings. How can you force an electron to go on, to stay on a circular path? Since the electrons have a charge, you can use magnetic field. So these green elements here are called bending magnets. They are part of the storage ring, and their function is to keep the electrons moving on a near circular path. Okay? On the straight sections of these rings, normally, they introduce other kind of magnets. Yesterday, you have seen undulators that were multiple magnets. They are normally introduced in straight sections because they can give to the radiation produced different properties. So the bending magnet is just a dipole. The undulators, and these are called wigglers, are multiple structures. But the effect of bending the beam and in using it to produce a circular part is given by bending magnets. This is one of the bending magnets of Daphne. That is the storage ring that we have here. Probably someone told you that Daphne is a very complex machine. It's not a single ring, it's a double ring machine. There are electrons running on one ring, positrons on the other, and then there are interaction points where electrons and positrons can collide. Okay? In our case, to produce synchrotron radiation, we use only the electron beams. Okay? So only the storage ring where electrons are circulating. Why I want to show you this? Because if you give a look, if they give you the chance to give a look inside the building where Daphne is hosted, you can see here are the magnets. This is the bending magnet. Then you have quadrupoles, sextupoles. These are used to focus the beam. And then, tangential to the trajectory, you see this. This is what is called a beam line. They're tubes made by stainless steel inside vacuum, and photon beams just run inside these tubes and can enter our laboratories where we can use them. Okay? What is an important thing to look about concerning bending magnets? The emission of a bending magnet, this is a spectrum where I report photons as a function of energy. You have a continuous emission going from infrared up to X-rays. What changes between a machine like Daphne? The energy of the electrons in Daphne is 0.5 JeV. let's say the energy of electrons in a machine like ISRF at Grenoble in France is 6 JeV. What changes moving from a low energy machine to a high energy machine? The critical energy, this knee here. You have half of the power emitted at an energy lower than the critical energy, half of the power at an energy higher than the critical energy. And this critical energy moves to higher values as a function of the square of the energy of the electrons. So, in my case, 0.5 JeV squared gives me something like 200 evolts. So in Daphne, this knee is at about 200 evolts. So this means that I can work, let's say, roughly up to 2,000, 3,000 electron volts. At ESRF, this knee is at 19 kilo electron volts. They can work something like 10 times the critical energy, so they can reach 190 keV. You understand? They are moved to hard X-rays. Here we can just move in the soft X-ray region. Okay? If there's something that you don't understand, please make me questions. I can stop. Because it's important. I don't want to tell you many things. Let's say few, but you understand them. Okay? So if there's something that is not clear, please ask me. You have seen these pictures yesterday. Here you have, here you have your bending magnet. Here there are the undulators. As you can see, light is emitted in the undulators because you have your beam-making wiggles induced by the multiple magnet structure, and beam produced by the bending magnets. All these beams can be collected and used to perform experiments. This is looking from the height. So you accelerate your electrons. The radiation produced in the undulator goes straight. The one produced by the bending magnet is collected by tubes, by beam lines that are tangent to the trajectory. This slide is important because it shows you the difference between the emission of a particle that moves on a circular path when its speed is lower than the speed of light, or when its speed is near the speed of light. What do you see? What is your impression? What is the main difference between these two emissions? What do you observe? What do you observe?
The left beam is very focused, while the right one is more like a cone that is expanding, but with not such a high area.
Great, that's it. The emission in this case, is concentrated in a near cone with a very small source size and a very small angular divergence. So this can be defined a bright source, this not. Other question, give a look here. Here is the power of synchrotron radiation emitted. As you can see, it depends on the energy. So what does this mean? The fourth power of energy. So do you think that the power of a machine like ESRF that is 6 JeV and the power emitted by a machine like Daphne that is 0.5 JeV are the same? There are many order of magnitude difference. Is it clear to you? Fourth power of energy. Another important thing. Here you have that the power there's an inverse proportion with mass. So do you think that is better to accelerate electrons or protons to produce synchrotron radiation? What do you think about? Electrons or protons? We said before that the mass of protons is 2,000 times bigger than the mass of electrons. So what would you put here? Electrons or protons to increase the power emitted? Perfect. Electrons. This is the reason why accelerators to produce synchrotron radiation normally are accelerate electrons or positrons that are electrons with positive charge, but never protons. Normally, protons are used in high-energy physics machines. Why? Because the emission of synchrotron radiation is very low, and they don't want to lose energy with the production of synchrotron radiation. In machines built to use synchrotron radiation, you need to accelerate electrons. Okay? This is very important. Keep this in your mind. Okay, let's go on. So, what kind of properties synchrotron radiation has? It's polarized in the plane of the orbit where it is emitted. It has a time structure, and it has a continuous emission. Why is this important? Probably, I don't know if you ever have seen X-ray tube, conventional X-ray source. Someone show you a picture of a conventional source. Normally, it has only two important wavelengths. The one related with the target you use to, with the target used, normally it's copper, so you can see K alpha and K beta of copper, and in that case you have a huge amount of photons, but the continuous part of the emission is very, very, very low. In this case, you have a huge amount of photons over a wide energy range. So you can make experiments where you need to scan energy. You're not limited only to one wavelength, but you can choose also a range of wavelengths because you have them all. This is just to show you the difference between the brightness of different light sources. A candle, a light bulb, this is a X-ray tube, this is sun. This is a bending magnet of a storage ring in the United States, and this is the brightness of an undulator on the same machine. I don't know if you're able to read the numbers here, but here we are, 10 to the 19 photons per second per millimeter square per radian square. And here we are, 10 to the 4. Do you realize the difference? Okay. So this picture now probably seems to you more familiar because, you know, we have the storage ring, and here are all the beam lines that are normally tangent to the trajectory because you have seen that the emission is tangent. So beam lines must be in this position. And beam lines are normally complex because you have different touches, one where you put the optics, another one where you put the sample, and in the last one, normally there are computers to control all the experiment. Just to, short story, because it's interesting. Just to know the theory about the possible presence of synchrotron radiation light is of 1945, made by Schwinger. The first time that synchrotron radiation light was seen is in 1947. The theory was there, but they could see it only years later. Why? Because since these machines are producing a lot of gamma rays, neutrons, and so on, they were letting electrons run in chambers made of glass. And so there were a lot of screens, concrete screens all around the machine, so it was impossible to see anything. What happened here at the General Electric in New York? Since they had some troubles, they decided to remove the screen in front of the machine, put a mirror in an angle up, and to be able to see, staying in the control room so far away from the machine, what was happening to the place where the electrons were running. At a certain point, one operator running the machine saw a huge light on this mirror, and he just turned off the machine because he thought it was burning. Then, since 2 weeks before, Schwinger went there to give a talk on synchrotron radiation, They thought, but isn't this synchrotron radiation? And it was that. And the reason why this kind of source has this name is because the first time it was observed was on a synchrotron. So this is the reason why it is called synchrotron light. At the moment, we are not using any more synchrotrons. Why? As Massimo told you yesterday, synchrotrons were working in this way. You were accelerating particles. Their energy was not fixed. They was just, each turn the energy was increasing. When they just reached the final energy, particles were extracted and sent on the target. But this was a not very efficient way to accelerate particles. The energy given, the energy of the particle was something like the square root of the energy of the machine. So here in Frascati, Bruno Tuschek thought about another kind of machine that can be used for energy physics. The same principle on which Daphne works. You have two rings, one where you have electrons, the other one where you have positrons. There is an interaction point, and here your two beams can collide. The energy of the particles is 2 times. It's the energy of one beam and the energy of the other beam. And this for us was perfect. Why? Because in this case, the electrons have a fixed energy. So this means that their trajectory is always the same. Their emission is always the same. So this was a good goal for high energy physics, but also for synchrotron radiation activities. Here in Frascati, there was, between 1959 and 1975, a synchrotron. Then here is ADA, the first storage ring realized on the project of Tuschek. ADA means anello di accumulazione in Italian, but in English it's just storage ring. After ADA, they built Adone, that in Italian means big ADA. Okay, this was only, but it's also a mythological person. Okay, but Adone was removed in 1993, and then came Daphne. In the field of synchrotron radiation, we are now at the 3rd generation of storage rings. And look here. In the first generation, we were using in parasitic way machines built for our energy physics. The brightness of the beams was between 10 to the 10 and 10 to the 14, just a little bit higher than an X-ray tube. Moving from the first to the 2nd generation, starting to build machines that were dedicated to this kind of activity, there was an increase in brightness. Improving the projects to realize this machine, including new undulators and so on, brightness increased up to 10 to the 22. So what we can register is an increase of a factor 1,000 in brightness every 10 years. And it's not the end, believe me. What happens is that this increases as this gets better. So this means that you can realize beams with very small source dimensions and very small divergence in the vertical and in the horizontal plane. This is ESRF, is the 6JB machine, one of the first 3rd generation machines. It has something like 64, I don't remember the exact number, of beamlines. So imagine around this, in this building here around, 65 beamlines, all tangent to the trajectory, all working together on different fields: chemistry, cultural heritage, biology, medicine, and so on. As a function of let's say, the emission from the bending magnet, wiggler, undulator, or free electron laser, you had this news yesterday, changes the shape of the emitted energy. In this case, if you have photons emitted along all the bending magnet, you have a huge horizontal dimension of your source. With wigglers, this is reduced. With undulators, this is further reduced. And with free electron laser, you have very, very small beams. And this gives you an increase in brightness. I told you that we're not at the end, because in the last years, first of all, there was a start coming from Max 4 in Sweden. They made the project to realize what is called an ultimate storage ring. You have seen before that if you have a long bending magnet, you have a long horizontal dimension because your emission comes along all the bending magnet. But if you reduce the bend, not including one dipole, but putting a huge number of small dipoles, one near the other, you reduce also the horizontal divergence and dimension. So what they're doing at ESRF, they already had a double bend, let's say, bending magnet made of two dipoles. Now, they will shut down in 2019, and in the same place, fix a new system where they have 7 bends. So the early bending magnet first became 2 bends. In the future, this will have 7 bends, whose function is always that to curve and to keep the beam on its curved trajectory, but reducing the horizontal divergence. So as you can see, their brightness will increase because they will move in the horizontal plane from 5 picometers to 0.169 nanometers. And if I reduce this emittance, I reduce dimension and divergence, and I increase brightness. This gives you an idea of the face. This is ESRF, this is Diamond, a storage ring built in UK. This is Alba in Spain. This is Max 4 in Sweden. This is not under construction. This has been constructed and start working. This is Sirius in Brazil. This is SSRF in China. Storage rings represent the 3rd generation of synchrotron radiation sources. Yesterday, Massimo showed you free electron lasers. You have seen that in this case, electrons are not bound to atoms and molecules. They can move inside these meters and meters, 100 meters of undulators, and emit the radiation. And the difference between their emission and the emission of a storage ring is coherence. These beams have very high brightness and are coherent. This is the first X-ray free electron laser that was realized at Stanford, LCLS, made a lot of very nice experiments. It started working in 2009. But now we have also an X-ray free electron laser in Europe. This is the XFEL, the European XFEL. Then there is also one SACLA, this other one, and one being built by in Switzerland. And again, we are not at the end, because as you have seen yesterday, we are waiting also for a 5th generation of synchrotron radiation sources, and these ones are represented by the ones you have seen yesterday. If you can reduce the dimension of a free electron laser from kilometer to meters, you can produce new accelerators that you can have in your campus at your university and perform in-house all the experiments some of the experiments that I will show you later. In Europe, these are the synchrotron radiation facilities that you have all around the world. These are the European ones. And if you're interested, if you want to learn something about their activity, the energy, and so on, there are these web pages where you can find all the news you want about them. As I told you, also here in Frascati, we have a small ring. We use it in parasitic way. Let's say that the main experiment that runs is a high energy physics experiment. We run only in a parasitic way, but our buildings are nearby Daphne, the building of Daphne. If you go and see the scheme, here we have 5 beam lines. We can go from infrared to UV, XUV, and X-ray. Clearly, our X-ray region, as I told you before, is limited to about 3,000 electron volts. So here we can study only light elements. But we can perform many different kinds of spectroscopy. Imaging in the infrared region, absorption, let's say study the atomic structure of the atomic structure of materials, study molecules, study surface effects. All this we can do also here in Frascati. Now, let's stop with machines, okay? Let's try to see what we can do with these beams. And since I told you that I want to show you applications with X-rays, we have to understand how is the interaction of X-rays with matter. You will know this. When light, and we can speak about light with any kind of wavelength, encounters an object, you can have many different effects. You can have, beam can be transmitted, reflected, absorbed, refracted, polarized, diffracted, or scattered. Okay? This happens also with visible light. But let's try to understand some of these, what they mean. Okay, let's go back to this electromagnetic spectrum. When we speak about radio waves, you can hear radio waves staying at home and hearing your radio. Why? Because this kind of waves are not absorbed, can go through, and then are captured by your radio and so on. But as the energy, you know, we said that wavelength decreases, energy increases. As the energy of the photons increases, what happens is that radiation is absorbed more and more strongly. This is also can be understood. Let's say, if you want to make a radiography of a broken bone, can you use visible light? What do you think? Can I see a bone with visible light? Here we are in visible light. Do you see my bones? No. Why? Because visible light cannot penetrate. It's absorbed at the surface. If I want to see my bones, I need to use photons with higher energy. So they need to penetrate and reach my bone, be absorbed, and I can make a radiography. Okay? How does absorption work? You just send light on a target, and if this light has a correct threshold energy, you can knock out electrons. And you can check that light is absorbed because you can measure a current. If you have here differential potential, you can measure the current produced, and you can see the number of electrons produced by your light impinging on the metal. But this does not happen for any kind of light. Look here. In this case, you have a potassium surface. To knock out electrons on the outer orbitals, you need an energy of about 2 electron volts. You send red light, the energy is 1.77 electron volts. Nothing happens. Here you send green light, the energy is 2.25. This is over 2 electron volts. So you have the production of 1 electron, photoelectron. Here you have, I think it was blue, I don't remember, light, 3.1 electron volt. You knock out all electron. Only if your photons have the energy that is reasonable, not reasonable, exactly the one you need to knock out your electron, this happens. This could not be explained by classical physics, but was explained by Einstein because he had also a Nobel Prize on photoelectric effect. You can imagine light as photons, these particles with their energy. They reach the atom, and if they have an energy that is enough to make one of the electrons of the atom free, this is okay. Otherwise, there's no kind of an interaction. So it's important, the energy of the photon. As I told you, with X-rays, we don't stop to the surface, but we go deep inside the material we want to study. And we can reach the electrons that are near to the nucleus of the atoms we want to study. So we are not making free electrons of the F shells that are very far away from the nucleus, but we are speaking about electrons that are on the 1s, 2s, 2p. These are the orbitals of the atoms that are the ones that are more near to the nucleus. So here you need very high energy. So what can happen? If I have my synchrotron radiation source, here I have a monochromator. What is a monochromator? I showed you before that the light emission is very huge. You can go from visible light to X-rays. But if I want X-rays only, how can I select them? With light, what can you use if you have white light and you want to separate colors? You can use a prism. You know a prism? That can give you monochromatic radiation. But that doesn't work with X-rays. With X-rays, we use one of the possible interactions of X-rays with matters, that is diffraction. You use crystals. You send your beam on the crystal as a function of the angle at which you orientate your crystal. You can select the energy that you need using what is called the Bragg law that I will show you in a few minutes. So, here I put my monochromator. I have a detector that tells me the number of photons that are arriving. Here I have my sample. My sample absorbs part of the radiation. Part of the radiation is transmitted. If I take the log of these two signals, the ratio of the log of these two signals, I can measure the absorption of that material. And look what I measure here. These are absorption spectra taken here in Frascati of sulfur. Sulfur that has different neighbors. Let's say around the sulfur atom, in all these cases, you have oxygen. But the number of oxygen atoms is changing. And from this spectra, you can see changes. So this means that these absorption spectra are the fingerprint of the structure of your material. From this kind of studies, I can understand the kind of atoms that surround the atom you want to study. Let's say, in this case, sulfur. Around sulfur, what is there? There are oxygen at a first distance. Let's say other sulfur, other oxygen at other distances. With this kind of spectra, I can tell you exactly the number of atoms that are at the first distance, at the second distance, and so on. So I can determine the local structure of the material I want to study. And this is possible because I'm using X-rays that can penetrate and interact with atoms. Since I will show you also some application using X-ray fluorescence, I want to explain you what is X-ray fluorescence. We spoke about the photoelectric effect. This is your atom. Here is your photon arriving. This is one of the electrons of your atom. This photon has the energy to knock out this electron, and it produces a photoelectron. This means that in this point where there was an electron, there's not more an electron, but there's a hole. Photon incoming. Here there was your electron. Your photoelectron is free to go away, but your atom now is unstable. So what happens? that an electron from another orbitals falls down here to fill this hole. And in doing this, there is the production of photons. So fluorescence is nothing else than a decay effect. You create a hole, electrons from other orbitals fall in this hole. While they're falling, they emit energy. And at the end, all your system goes back stable. And this happens practically at the same time. You don't see this effect. But why is this important? Because while using absorption, I can tell you everything about the atomic structure of the material. If I just want to know what kind of atoms are in the material, you come here and you give me your sample. And you tell me, oh, what atoms are here inside? What is the fastest way to give you this answer? The fastest way is fluorescence. You just put it on an X-ray beam. Since fluorescence is the energy of the fluorescence peaks produced is proportional to the atomic number, each atom has its own fluorescence lines. So if we have a material that contains calcium, zinc, lead, I can measure the lines that are coming from zinc, lead, and so on, and the height of these peaks can give me also information on the quantity. So I can make, with fluorescence, you can measure the atomic composition. So I can tell you what kind of atoms are inside the material. Not if they're oxidized or metallic and so on, but I can tell you what kind of atoms are inside my material. As I told you before, many kinds of processes can happen, but in the energy range that we can take into account, the highest probability, so the effect that have the highest probability to occur are photoelectric effect and scattering. And this is the reason why we use, as a function of these effects, we can send our light to this black box that represents our sample, and as a function of the different kind of technique I want to use different detectors, but also achieve different kind of information. I can use imaging, because here what I do is I use absorption. I can use diffraction and also give you information, use this with the Bragg law to monochromatize beams, but use this also to have information on the atomic structure of crystalline materials. Or I can use absorption and measure absorption edges and give you information on the structural organization and so also on the properties of the material I want to study. Alors, before going to application, is it clear? You have an idea? So, the most important thing is this. With fluorescence, you can say something about the atomic composition of material. So you can say what kind of atoms are inside your material. Okay? With absorption, you can study the structure, how your atoms are organized. With imaging, you can have information on structure that are able to absorb and so give you information that can be used also for medical applications and so on. These are the examples that I want to show you. And we can start with cultural heritage. Just give a look to this painting. This is a painting of Van Gogh. This is called The Patch on the Grass. You see this red square here? Under this grass, also, if it doesn't seem that possible, if you make a radiography of this painting, look, this is done with conventional X-ray. Do you see something? This is done with infrared. It's possible to see something, no? This painting was analyzed at the SRF. And they excited the fluorescence of elements contained in colors. In this case, lead, antimonium, mercury, zinc, because they were contained in yellow, vermilion, and so on. And then, this is just a map of the presence of these elements in the square. Then, knowing the colors of each kind of these elements in the painting, you can reconstruct this. Here, you excite the colors because you are exciting different elements and you measure fluorescence. Here, you put all your information together, giving them a color, and you can see what is behind this. And what does this? These are faces of other paintings of Van Gogh. Why is this important? This is important because it tells you two things. Van Gogh was very poor, so he was using the same canvas also to make some trials of his paintings. Then, when he had some orders, he really used the canvas to produce what was asked, or what he wanted to paint. But this is important also because probably these designs come from the early stage of his, let's say, career. So you can also learn something about the evolution of Van Gogh. And this is behind this. If you go to the museum, you see this. If you look to this with X-rays, you see also what is behind the grass. This is another important application. Probably you know about the Pompeii, that is a city near Naples, where there are all these buildings that were destroyed by the eruption of the volcano Vesuvius. And what is happening in time is that these red walls are becoming black. And this is a big problem because it means that painting is being altered. So it's important to understand why this is happening. Because if you want to preserve this, you need to understand what is happening. So these are studies that have been done, and they have seen that the color, this cinnabar, is the sulfur contained in this color, is getting oxidized. And so you move from red to black. And how can you understand this? You can understand this using absorption measurements, where you can study different kinds of compounds and try to understand which one is comparable with what you find here. And if you know what is happening, you can also give information that can be used to preserve these walls. But you understand that to make this kind of studies, you need to have a continuous source of soft X-rays, and this can be done only using synchrotron radiation. This is another masterpiece. This is the Palimpsest of Archimedes. This book was written about 1,000 years ago. It was written on parchment. Clearly, when it was written, it was a very important treatise. But then, with time going on, what happened? This book was used to become a Christian prayer book, because parchment is very expensive. So they just, let's say, scratched away ink, and they painted over the pages prayers and also gold layers. So all the things written by Archimedes were destroyed. But this book disappeared in a part of history. And then it was bought in 1998 by a person that is anonymous. And he paid for this book $2,200,000. And he gave it to the Baltimore Museum that is now trying to restore it. The person who kept this book before selling it kept it in mold. So you can see it's very damaged. It's a pity, but something can be done. At Stanford in the US, since the ink used by Archimedes contained iron, it is possible, using X-ray fluorescence, to read what is under gold. So it's possible to analyze all these pages, also if they're covered by gold, and reobtain what was written by Archimedes. Okay, stop with cultural heritage. Let's move to paleontology. Look here. This is a piece of amber. It's a little bit old. It has only 1 million years. Okay, so we can imagine when it was produced, long, long time ago. If you look this amber with X-rays, with a conventional source or with infrared, you can see some small structures that were, let's say, glued by amber while it was, let's say, getting stronger and stronger. And what is included here inside is something that has the same age, 1 million years. Okay, at ESRF, using X-rays and X-ray tomography, they can reproduce, can make a 3D reconstruction of all the things that were inside amber. So we have images, 3D images of insects that have only 1 million years. These are only 1 million years old. So we can have something that is important for biology, for who studies this kind of things. And these are not the only things that are being studied. They study also many other kinds of fossils. And if you go on the web pages of ESRF, there are many interesting applications and research that have been done. And you can see them, and believe me, they're very interesting. So I put here, previously, I think here there was, it's missing, but you only have to write ESRF news, and you will achieve all the past and the present news that are being sent around by this facility. Do you think that we can use synchrotron radiation also to study food? Probably yes, because also food is made of atoms, no? And probably you don't believe me, but there are a huge number of studies made on chocolate. You want to know why? Look here. This is normal chocolate. This is that white layer. I don't know if you ever bought a chocolate and when you open it, it's a bit white. That doesn't mean that chocolate is not good. But clearly, you don't want to eat it because you expect something brown and you see something white. And this is a very big problem that has a lot of companies that produce chocolate. Because if they produce it and then there is this kind of evolution, they don't sell it. And what was studied is that inside chocolate, you have different kinds of grease. And the presence of this white layer comes from the crystallization of this grease matter inside chocolate. So they can find a way to do this crystallization more softly to avoid this. And this is a lot of money. Using diffraction, you can study the structure of chocolate. Biocrystallography. Also, this is very important. Why? Because using X-rays, let's say physicists can give information that are very useful to produce medicines. And this is just to show you, if you want to understand if a drug can be used or not, or can be useful or not, you really have to understand the structure of the biological things that interact with the chemical elements of the drug. So this means that you have to have information of the structure of all these biological things that can be proteins. Before the presence of synchrotron radiation, the number of structures that were solved from 1972 up to 1990 were very small amount, lower than 10,000. With the presence of synchrotron radiation and X-rays, with these new sources, the amount of structures that have been studied increased very much. You can see there's an exponential increase. And also the complexity of things that could be studied. In 50 years, we went from myoglobin up to ribosomes. And these are very, very complex systems, but it's very important to know how atoms are organized inside a ribosome, and I will show you also why. Look here. This is a table. It's updated to 2016. These are the structures studied by synchrotron radiation. This is the total number of structures resolved, and this is the orange part is the part given to synchrotron radiation. We are over the total number. I don't remember how much it is, but the number increased very, very much, thanks to the fact that we have very, very bright sources. And this brought also to the possibility to have Nobel Prizes taken by people working also using synchrotron radiation. In this case, Professor Jonath made measurements at the SRF, and all three of them got the Nobel Prize because they were able to solve the structure of ribosomes. And ribosomes are important because they interact with antibiotics. If you don't know how this works, you're not also able to understand how to produce something that can have an efficient effect on us when we have diseases. Quanto c'ho ancora? Ho finito? Okay. Let's jump to the end. I'm sorry, it was a bit long. But I hope that I was able to show you that synchrotron radiation sources are very important, are useful, can give you a lot of information in many different fields. And X-ray studies can give you information in fields like biology, medicine, cultural heritage, solid-state physics. And this is possible only because a huge number of people worked to have such wonderful sources. Thank you for your attention.